Okay guys, today we'll see about propellers. Okay, so as you know, propellers are vital to produce thrust, being one of the efficient ways to create thrust. Because of a lot of drawbacks, we don't use much of propellers given in small aircrafts, or like where you're not going very long, or you are just when you're traveling small distances or carrying small passengers, not small passengers, like small group of passengers. Okay, so obviously aircraft uses propellers, and the power required to run the propeller can be any type of engine. It can be internal combustion engine like the piston engines, or it can be a jet engine. This is not a jet engine, I think it is not a jet engine, so it can be turbojet engine. And your propellers can even drive ships. Okay, when propellers are used to drive ships. So let us see how the construction of a propeller is. Okay, so this is your typical propeller. So it has got a leading edge, a trailing edge, a root, a hub, and the tip. So your propeller is basically made up of airfoils. Okay, so it is stacked airfoil. Okay, so it has got, see, if this is one airfoil set, another airfoil, so it is stacked one above each other. Okay, and at the tip your propeller becomes so thin that it doesn't really produce any thrust. Okay, and even at the root, that is this part, because of a structural constraint, or to hold the propeller, it almost becomes it loses the airfoil shape, and it almost becomes like a cylinder. Okay, so the only thrust producing place, or lift producing, which is actually the lift, so lift producing place would be the leading edge and the trailing edge, and hub is nothing but your shaft, whichever is driving. Okay, and then again this shaft is powered by an engine. It can be IC engine or it can be jet engine, some sort of engine. Okay, and by thrust equation we know that thrust is equal to mass flow rate into difference of velocity at the exit minus the velocity at inlet. So the propeller, basically what it is doing is it is just accelerating a mass flow rate from a differential velocity. Okay, you have some mass flow rate, the propeller is simply increasing that mass flow rate and then moving it to obtain thrust. Okay, so that is the basic idea behind propeller. Okay, so then this is your propeller design for an aircraft engine, in an aircraft. So you have got, so this is not a cut section, this is a complete propeller from side view, or you can say top view. Okay, so this is the first airfoil, and that is at the aft of the propeller. Okay, this airfoil at the aft, and this has got a twist. Okay, so this has got a twist, and if you draw a central line to this, this is your beta tip, that is from this airfoil is producing an angle of beta, and the one at the aft is producing an angle beta root. Okay, so this is called angle of twist. Okay, and this is your leading edge and this is your trailing edge. We'll see why this twist is important when we come to the working part of it. So like how, just some basic idea about what is an airfoil. So you know, airfoil is produced extensively. I mean, airfoil is important feature for an aircraft to produce lift. Okay, so this airfoil is generated by different research committees. Okay, so what they do is they just plot an airfoil. So these are the different data points of an airfoil. Okay, on an XY axis they'll take, and they'll plot different data points or different points of the aerofoil, and then when you plot, you obtain a geometry like this. Okay, and then they do extensive research on it, and then they finally plot for what angle of attack, what is the corresponding CL and CD, that is coefficient of lift and coefficient of drag. That is nothing but lift divided by the dynamic pressure. Okay, so they generate firstly they'll design the airfoil, and this is the structure of that airfoil, and this is how it behaves for different angle of attacks, and what is the CL and CD. So CL and CD will, since it is divided by dynamic pressure, it will incorporate directly relate to the flight velocity. Okay, so one such research is done by the National Advisory Committee for Aeronautics, which is the NACA. They produce numerous number of NACA series. So your present day aircraft, many of it still uses the airfoil manufactured, not manufactured, the airfoil designed by this NACA. And here we'll see how the blade interacts with the incoming air. So in a typical airfoil, what you know, the velocity is coming. So if you have your wing airfoil section, so if it is a wing, your V infinity or the incoming air will be in this direction. Okay, but if you take a propeller, okay, so this is the hub that is connected to, and your propeller rotation direction is like this, correct? So the incoming air will be at this, okay, will be normal to the blade, okay, will be normal to the blade. So this is your V infinity or your incoming air V naught. Okay, and also the propeller is rotating at certain speed omega. Okay, so that is your V2. Okay, the resultant velocity because of this will be your V1. Okay, I mean the resolution of these two is V1 like this, and the angle of attack is produced here. Okay, from V1 to a geometric line, to a geometric central line of the airfoil. Okay, so if you take a wing, I think this would be your angle of attack, the complete angle would be your alpha. Okay, but that is not the case if you are considering it as a propeller. Okay, so this is how you obtain it. And the distance between the 0th position and your V0, sorry, and your angle of attack will give the geometric pitch. We'll see how to measure pitch in a propeller probably in the next slide. And this is your actual pitch. So that is your V0. The height of your V0 will be your actual pitch. Okay, so this is your propeller pitch. So propeller pitch, how do you measure propeller pitch is, let us say this is your airfoil, so this is your propeller and it is moving in this direction. Okay, if you consider this point, if you consider this point and the propeller is taking one complete resolution, so if it takes one complete resolution, the amount it has come forward will be your pitch or your geometric pitch. So if it is not attached to any aircraft or any sort of mechanism, so if you just let us say you have a screw thread here. Okay, you have a screw thread here, it has got it has got an external thread and the propeller contains an internal thread. Okay, and then if you move the propeller on that screw thread, the distance, the horizontal distance covered by the propeller is your pitch. Okay, so coming back here, so this line will give you the actual pitch, but because it is placed on an aircraft and it has got many other forces acting on it, the drag and all and all those things, your actual pitch is slightly reduced. We'll see what are the factors that how this comes into picture. Okay. And here to give you an example of how I mean this various parameters on a two dimension you would not understand it, so we'll see a small video on different propeller parameters.
Nowadays, propellers are taken for granted. But how do they work? It's important to know, because they produce effects that influence aircraft behavior and the way we fly them. Remember that the Wright brothers appreciated that the basis for propeller design was the same as for wings, the subsonic aerofoil. When moving through the air, it generates a total reaction, which enables an aircraft to fly. This is best explained by looking at it in terms of the lift produced by the aerofoil and the drag created by its resistance to the air. If the angle of attack is increased, more lift is generated, but at the expense of increased drag. Maximum lift being produced at the point of stall. A wing is usually at its most efficient at a relatively small angle of attack. In very simple terms, a propeller or air screw is really two or more rotating aerofoils set to pull the propeller through the air, in the same way as the thread of a screw pulls it into wood. During flight, its motion will comprise rotational velocity and forward velocity. With the propeller stationary, any forward velocity is that of the aircraft, the true airspeed. But a rotating propeller accelerates air and produces the induced flow. The sum of the TAS and the induced flow is the total inflow. Now the direction of the relative airflow can be plotted. But we know that to work effectively, aerofoils have to be set at a small angle of attack. The angle between the chord line and the plane of rotation is known as the blade angle or pitch of the propeller. The rotational velocity at the blade tip is faster than near the hub. And if the pitch remained constant, the angle of attack would increase towards the blade tip, possibly causing it to stall. So the blade is twisted to maintain a constant angle of attack. This is a fixed pitch propeller. It generates a total reaction in the same way as a wing. We know that the amount of lift generated varies with the angle of attack. It also varies with the speed of the airflow. The faster the airflow, the greater the lift. And vice versa. So in order to maintain level flight, when pilots alter an aircraft's speed, they also have to adjust the angle of attack to keep the lift constant and equal to the aircraft's weight. But whereas the speed of the airflow over a wing aerofoil is dictated by the speed of the aircraft, the airflow over a propeller is governed by its rotational speed, which is much faster than the forward velocity and virtually constant. Consequently, changes of forward velocity have very little effect on the speed of the relative airflow. What is affected by changes of forward velocity is the angle of attack and the consequent strength and direction of the total reaction produced. Remember that the total reaction produced by a wing aerofoil can be resolved in terms of lift and drag, and that the penalty for increased lift is increased drag. With a propeller, the total reaction is resolved as thrust, the force needed to overcome the drag of the airframe, and the propeller drag, or torque, which balances the power output of the engine. The penalty for increased thrust is increased torque. When a propeller is turning at a constant speed and the aircraft is stationary, the angle of attack is big, and large amounts of thrust and torque are produced. As the aircraft accelerates, so the angle of attack decreases with a consequent loss of thrust and torque. This continues until the reducing thrust equals the increasing airframe drag, when the aircraft has reached its maximum speed. The principal limitation of fixed-pitch propellers is that there is only one speed at which they work at peak efficiency. This propeller is a fine-pitch propeller, giving good performance for takeoff and climbing, but a relatively low maximum speed. By increasing or coarsening the pitch, the maximum speed can be increased, but there are practical limits to the size of the blade angle that can be used, since too large an angle might mean the propeller could be stalled when the aircraft is stationary or moving at low speeds. Torque would be high, so RPM would be low, and because the direction of the total reaction is further from the direction of flight, less thrust would be produced, and acceleration would be too slow for takeoff from normal airfields.
So the conclusive remarks of that video would be how the velocity of the aircraft will impact the angle of attack, and why is there a need for the blade twist. Okay, so it means to say that if at all your propeller was without a twist, the angle of attack at the tips would be very huge compared to the root. So that would be very huge, such that it will stall. Okay, to prevent that, you are giving the twist to the propeller blade. That will counterbalance, and even though at the tip the angle of attack throughout the propeller will remain constant. And that is about it. I hope you understood the whole. I think the main idea behind this video was to see how, to visualize it, how different the airfoil behaves as opposed to a wing airfoil and a propeller airfoil. So next we'll speak of types of propeller. For your syllabus point of view, you only need to know 3 of it: the fixed and the constant speed, and one more would be variable pitch. Okay, so but one of your classmates have sent me a link which has got different types of propellers, so we'll see it. So fixed pitch is one designed propeller. Okay, it won't have any, you can't change the pitch once you design it, and that's about it. Fixed pitch propeller. So the problem with fixed pitch propeller is that you can't change your pitch, which is very much necessary to control the angle of attack at different cruising points, different flight conditions. Okay, and then your metal propellers, that is the propellers make use of metals. It's manufactured using metal. Formerly only wooden propellers were used when the propeller engine came out. Wooden propellers were made because it was easier to stack them or manufacture them in this way, because like I said, it is stacked, the airfoils are stacked. This was a better option. And then later on we moved to metal propellers, and right now there has been studies going on to make composite propellers, which makes use of composites, so that we can use the propeller engine. One drawback of the propeller engine is that it can't move with supersonic speeds. Why? Because it will create flow suppression and then lot of boundary separation and disturbances across the aircraft. And to avoid that, we are making use of composites to manufacture sonic propellers, okay, which can work at sonic range. We know that propeller engine is very efficient compared to all others, and the range also. And to improvise that, we are trying to work on composite propellers. So ground adjustable propeller, one drawback of propeller, what we saw in the classes was the height. Okay, the overall height of the aircraft should be much taller compared to other engines, because the propeller will take more space in frontal area, so the propeller blade should not touch the ground. Okay, to avoid that, you can adjust the height of the propeller. Okay, then controllable pitch propeller, or called as variable pitch propeller. This is used. I mean, there is some mechanism to change the pitch of the propeller in flight of the propeller. I mean, if you are in flight during that time also, you can control the pitch and then keep it at the necessary angle of attack. Constant speed propeller, this one is an important one. So constant speed propeller is similar to variable pitch propeller, but only thing is the propeller will be driven at one constant speed. Let us say that the propeller works efficiently at 6000 rpm. The propeller will run at 6000 rpm at all flight conditions. But how do you manage the different flight conditions, let's say takeoff or landing or cruise conditions, even with a constant speed? That is, you change the propeller, you change the pitch of the propeller, and then try to manage those flight conditions, but keeping the propeller at constant speed. Keeping the propeller at constant speed has got many benefits to it. The maintenance will be very less compared to other times. And then we have this is similar to your control speed, but here what you can do is you can modify the blades, and if at all you have got an engine failure at any point on a multi-engine aircraft, if you've got an engine failure, you can modify any of the propellers to produce more thrust compared to the other one by adjusting the different parameters of the propeller. Okay, and reverse pitch propellers, these are used as your drag inducers. Okay, this is used like a braking mechanism, so they produce negative thrust, and then you can produce the brake mechanism in your aircraft. Do go through this all of it completely. I'll be sharing the link in the PPT, and then let's see. Okay, so the general thrust equation, what we have understood so far is thrust is comprising of two components. One is your pressure thrust, and your pressure thrust and momentum thrust. Okay, the most important one would be your momentum thrust, which is adding to your propeller, which is actually creating the required thrust. And pressure thrust is not that important. So with that, we know, like we discussed, it is given by ratios of mass flow rate into exit velocity minus inlet velocity. Sorry, I think I said mass flow rate, ratios of mass flow rate. No, it is just mass flow rate into difference in velocity. And we know mass flow rate of output is an addition of fuel, but fuel ratio is very small, so therefore we'll take it as 1, and that will ultimately come to the mass flow rate into velocity exit minus velocity inlet. Okay, so to design a propeller, or how it works, or how much of it you will have to consider, there is two theories. One is your momentum theory for a propeller, and the other one is a blade element theory. So momentum theory will just give you about how much thrust you can produce just using a propeller for a given diameter. Okay, if you have a propeller of a given diameter, how much thrust you can produce is what the momentum theory is talking about. It is not addressing any other issues, okay, compared to in a propeller, let's say whirling flow, or how the velocities are differing, and what are the different drag elements that is being imposed on a propeller, and all this it won't address. Okay, it is just simply saying how much momentum you can generate for a given diameter of a propeller. Okay, so the considerations here are, you'll have an inlet flow and you have an outlet condition. Okay, and then the propeller you have will simply be replaced by an actuator disc, that is a circular element. Okay, so if you see a propeller, so it will form a circular disc, correct? So your propeller is replaced by a circular disc, saying the circular disc will add up to the increased pressure. Okay, so basically what your propeller is doing, it is increasing the pressure of the incoming air. That is your dynamic pressure. Okay, so we'll come back to assumptions. So just it is increasing the pressure. Okay, so you remove or you replace the propeller with just a circular cross section, and then say after air passing through this cross section, the pressure whatever it is, that will be much higher, is what the momentum theory is trying to address, and we'll work out how it is working in here. Okay, so assumptions of momentum theory: propeller is replaced by an actuator disc, like I said, and the disc is porous and very small thickness. It has no mass. Okay, it has no mass, and it provides no resistance, zero drag on the flow, since it has no propeller blades. Okay, no abrupt change in velocity across the disc. Velocity is uniform and smooth across the entire disc. So a given velocity is fixed at that point of disc. Okay, and there is no abrupt change. It will increase or it will decrease. However, the graph is given. Okay, we'll see the graph. Since it's an actuator disc, it has to do something. Okay, it has to do something. So here what it is doing, it is doing some sort of work. Okay, what it is doing, it is increasing the pressure from P1 to P2 on the working fluid, that is your air. Okay, and one more assumption: the working fluid is incompressible. However, it is assumed to be irrotational before and aft of the disc. So that is it. That is, it can't have any irrotational to it. It may or may not have any irrotational in the disc. Okay, and the static pressure at far upstream and far downstream is equal to the atmospheric pressure. However, the velocities at these points are different. This point I'll show you in the graph. So let us say you have a pressure, an inlet pressure of PA or P infinity or P naught, however you want to take P naught. So when it is coming towards the disc, the pressure is reduced to P2, and then once it passes through the disc, it will increase, a drastic increase or a sudden increase or a step increase to P3, and as and when it exits, it will exit to a pressure of the atmosphere, whatever pressure you are maintaining in the atmosphere, and then the velocity is starting from V infinity or whatever the atmospheric condition is, and from there at the disc it will increase to a certain value, and from there it will increase to a maximum value at the exit point. Okay, this is a bit complicated for your in your textbooks or the references or the notes that I've given already. The derivation part is a little complicated. I'll try to simplify it down in this. So I've made some written notes. So this will be, so let us take into consideration as three boundary conditions. Rho naught is your density, and A naught is area at inlet, and A1 is the area of the disc. Okay, and A2 is your exit boundary condition, and P naught, which is P infinity, will reduce to P1 when it is nearing the disc, and after crossing the disc there is a step increase to P2, and at the exit it will come back to its original position P1. Okay, and velocity increase will be from V0 to V1 at the disc and V2 at the exit. So if you see velocity, there is no, it has uniform incremental. Okay, it is increasing uniformly as in how the assumptions made, and we have completely taken out irrotational flows. Okay, so this is considering some part of slip and irrotational flows. They have included B and A, which is not necessary for it will complicate things but end up to be the same values as how we would obtain in this method also. Okay, so I hope you understood the boundary conditions. So by continuity equation we know what is continuity equation? It will describe the mass flow rate in a given section is constant. Okay, so since rho naught is since the working fluid is incompressible, the density will be constant. So rho naught A naught V naught is equal to rho 1 A1 V1 is equal to rho 2 A2 V2. Since density is constant, we'll cancel it out. So it will be A naught V naught is equal to A1 V1 is equal to A2 V2. Okay, and then we'll apply the Bernoulli's equation. Bernoulli's equation from section 1 to 2 and then 2 to 3. So at section 1 we have P naught plus half rho naught V naught square, P naught plus half rho naught V naught square is equal to this point. So this point would be P1 plus half rho naught V1 square, rho naught V1 square. Okay, and then from this section to this section we'll have P2 plus half rho naught V1 square. So since V1 is the same on the disk, it is V1 square only. So P2 plus half rho naught V1 square is equal to P naught plus half rho naught V2 square. So that is your Bernoulli's equation. So you write it as equation 1 and 2. So after taking equation 1 and 2, you add both equations. So if you add both the equations, so I'm just adding P naught plus half. So P naught plus half rho V naught square plus the second part was P2 plus half rho naught V1 square is equal to P1 plus half rho naught V1 square plus P naught plus half rho naught V2 square. So adding both the equations, what you can see is you can cancel out P naught and P naught, and then half rho naught V1 square, half rho naught V1 square, and then you are left out with P2, this point, P2 minus P1, you'll take it to the other side, is equal to half, that is half rho naught V2 square minus half rho naught V naught square. So by taking half rho naught common, you have got V2 square minus V naught square. So this is your overall Bernoulli's equation across the tube. Okay. So now we know what is thrust given by. Thrust is given by F is equal to mass flow rate into V out minus V in. That is your exit velocity minus the inlet velocity. But what is mass flow rate given by? Your continuity rho naught A naught V naught is equal to V2 minus V naught. V2 minus V naught. Okay. And one more thing I forgot to mention. Since the actual increment here is, or the actual work the actuator is doing is, it is just increasing P2 and P1. So the consequence of this is actually the thrust. Okay. So the consequence of this incremental pressure is the thrust. So by losing pressure here, it is increasing the velocity. Correct. So then you have another, the thrust is developed using this pressure. So, but how do you write force in terms of pressure? Is force is equal to differential pressure into area. So P2 minus P1 into area of that actuator disc is A1. So this is thrust and force, this is force and this is thrust. We can equate these two. So P2 minus P1 into A1 is equal to rho naught A naught V naught is into V2 minus V naught. Okay. So now we'll try to reduce this. Since this is continuity equation, we know A naught and V naught can be written as A1 and V1. Okay. A naught and V naught is equal to A1 and V1 by continuity equation. So therefore P2 minus P1 into A1 is equal to rho naught A1 V1 into V2 minus V naught. Why did we use A1 and V1 instead of A2 and V2? Because we can cancel out A1 at this point. Okay, to cancel out A1 at this point, we'll make consideration as A1 and V1. So depending on how your equation goes, you can modify this mass flow rate value. Okay. or if you have or if you're solving a problem and they have not given you, let's say A1, they've given you A2. Okay, most times it is A1 only, but if they've given you A2, you can just use this condition and then solve how it goes. However it goes. Okay, so here A1 is preferable. We can cancel out A1. So by inducing or by adding A1 and V1, not adding, by inducing A1 and V1 here, we can cancel out A1, and then P2 minus P1 is equal to rho naught V1 into V2 minus V0. Okay, but from Bernoulli's equation, what we solved here, P2 minus P1 is equal to half rho naught V2 square minus V0 square. We'll now bring in that in place of here. So we'll substitute half rho naught V2 square minus V0. Okay. So this is the substitution. So P0 is equal to half rho naught V2 square minus V0 square. So rho naught V1 into V2 minus V0 is equal to half rho naught A square minus B square, A plus B and A minus B. So with this we'll cancel rho naught V2 minus 0, V2 minus 0. Okay, which will imply V1 is equal to V2 plus V0 by 2. So V1 at this point is given by V2 plus V0 divided by 2, which is an important result here. Okay, so I think your main idea is to obtain this equation. After this, we'll try to see the propeller efficiency. Okay, so propeller efficiency, which is also called Frod's efficiency, Fraud, however you want to say it. So we know propeller efficiency in general is given by thrust power by propulsive power. We have seen this in the derivation for jet engines. So thrust power is equal to what? But what is thrust power given by? Thrust into inlet velocity. So thrust is rho naught A naught V naught into V2 minus V1, that is mass flow rate, into V2 minus V1 into V naught. Okay. So now that will imply rho naught A naught V naught square into V2 minus V1. Again, if you want it, this can also be rho naught A1 V1, but this V naught won't get multiplied. So for convenience, we take rho naught A naught V naught, and that will become square. And propulsive power, or the input power, is the total kinetic energy. Okay, in terms of power. So kinetic energy in terms of power will be half mass flow rate. Okay, this is important. This dot will add the given time that is missing, so divided by second and convert this into power. So half m dot V2 square minus V0 square is equal to, again, so we've used half rho naught A naught V naught here, so we'll again take half rho naught A naught V naught into V2 square minus V0 square. So by substituting these two, we have efficiency, or propulsive efficiency, is equal to rho naught A naught V naught square into V2 minus V0 into half rho naught A naught V naught into V2 square minus V0. So again, A plus B into A minus B, cancel V2 minus V2, rho naught A naught, and V0 square will now become only V0. So this half will go up to V0 divided by V2 plus V1. So that can be written as 2 by V2 minus V0 plus 1, and then 2 by, that is the velocity ratio alpha, plus 1. Okay, this is one form of writing it, but we also know V2 plus V0 by 2 is equal to V1, which I said the important result before. And if you substitute this 2 below, if you take this 2 below, V2 plus V0 divided by 2 will now be propulsive efficiency given as the inlet velocity divided by the velocity at the actuator disc is also your propulsive efficiency. Okay, so this is, the whole thing is about momentum theory. So like I said, it is only talking about how much thrust can be obtained for a given diameter of the propeller. Okay, So since it is not addressing a lot of properties here, so this efficiency what you calculate is not the actual efficiency. So the energy lost in rotational motion acquired by the flow in passing through the propeller is not considered. Losses due to non-uniform thrust loading over the blade length, you don't even consider the blade, so I think that is a major drawback. Blade interference losses due to the interaction of flows over the neighboring blades, again that is not addressed. So I mean the blade interaction between two blades is not addressed. Propeller profile drag losses incurred over the blade surface, changes in flow properties due to effect of compressibility, which are not accounted for. So you might ask, we have got so many drawbacks of this, and yet why we stick to this theory is that because it will give you one general idea. Okay, one general idea of how much can be expected by doing simpler calculations. Only when you take it to the manufacturing level, you make use of the other theories, one which we'll discuss later on, that is your blade element theory, and then you addressed a lot of issues and then you finalize it. Okay, so depending on your requirements, you go about with the theory. So the momentum theory is addressing so much. So with this I would want you to, okay, we have one more here. So if this is the actual efficiency, okay, how, like we did see how the propeller will reach a maximum efficiency for a given velocity and beyond which how it will decline. So even that is not being addressed here. So this is the induced efficiency, or the efficiency obtained from your momentum theory, how it is varying and how the actual efficiency vary. So if you can see, this gap is not that big. Okay, so to frame out, or just to give a basic idea, if you had an area of or if you had a diameter of so much for a propeller, how much it would give, or what is the velocity ranges you can work. So to get basic idea, you can use that. Okay, so with this I think you should solve this problem. So just use the basic definitions what we have derived so far, and these are the solutions. If you don't get it, you can contact me directly, and then I've actually written the solution. If you are not getting it, I'll try to post it back. Okay.